Hi, thank you for joining our session today on image processing in Delta Lake. My name's Jason and Rohit. I am the Platform SME lead for Enterprise Platform Features at Databricks. And I'm joined here with my esteemed colleague, Rohit. Do you want to introduce yourself?
Thank you, Jason. Hi, all. I'm Rohit Gopal. I'm a solutions architect at Databricks, based out of Seattle, and my background is in data science and machine learning. And I'm excited to walk you all through what we're going to show here. Right back at you, Jason.
All right, so to kick things off, just going over a couple things. As we know, and we've seen, deep learning's come a long way over the past few years. And even our working with different types of data and images specifically, which is the subject of this talk, has improved. We wanted to share also the using images on Delta Lake and kind of how to do that in a way that's super efficient. Some use cases that I've worked through with various customers and departments, I get easily 45 times the improvement in various cases. So Rohit and I want to share this with you today. So what we'll go through is first we'll start off with a little architecture for an image processing pipeline, walk over some challenges, and then look at some various techniques for operating with images as kind of first-class citizens. So we'll look at that on Delta Lake. And then Rohit is going to cover training on using distributed models and looking at a couple techniques there. And then he'll show off a inference pipeline where your data scientists can actually bring in whichever model framework they need and still not have a operational code change in order to use those new models. So we'll show you those. Then we'll go over some limitations and sum up. So hopefully this will be useful for you and for your image processing pipelines. Starting off, architecture of an image processing pipeline. So maybe some sample use cases that we've seen this in. If you are already coming to us knowing you have image processing needs, then you probably already have this. But what we see this kind of across the board for defect and anomaly detection, sometimes even augmenting SCADA processes with more low-cost video sensors and such, and doing some processing on that in parallel to what's already in place. Identifying health issues. We see object recognition, face recognition, that's all over the place these days, as well as auto grouping and OCR. Lots of different use cases where you might need to really deal with images and not only deal with them onesie twosie, but at scale, which is what we're all about. So the pipeline that we're going to walk through today is really looks like this. So we are going to pretend that we have a batch or stream source. We're going to just use a pool of images, and I'll show you that during the demo. But typically you'll have your images come in, and they could be in batch or streaming use case. You'll likely store them, and then maybe have a queuing process to go and run inference based on your existing models. So classify them as it has an object, or it's this letter, or it says it should be grouped with these people, or has some sort of feature that you've extracted from the image. And then you'll typically then store those classified images and optionally set up some notifications that say, hey, we really want to look for this thing, notify us immediately, or just make it available for processing with those classified features. In a separate cycle, usually you'll have your actual training for the model and for your classification model. And so we've got that modeled here using MLflow. And in this case, you'll normally have a piece of training code. You'll pull that in. It may have different variants. Actually, Rohit will show off two different ones that we use for this demo. You'll want to serialize your model, and then we're doing this in Databricks, so we have the model registry kind of built in so that we can use and immediately mark whether it's production or not, so that the as the inference pipeline is running in production, it can immediately pick up the next version without any other changes. So this is what we will be demoing, walking through today. So just kind of starting off, and this is just said in more detail, the architecture of an image processing pipeline. So we've got the training and the inference. You're often going to run your training much less frequently than the images that you'll be inferring. So we have that set up here using MLflow again. And then training models can, in our version, can be deployed immediately to production. So we're using MLflow. We've got a special class of a model that bakes in some of the pipeline features that Rohit will show. And those can be Dockerized at the end of the day and taken to wherever you need if your actual need for classification is not even in the cloud. So we'll show you a little bit how to do that today. And then we'll also show you a switch between deep learning frameworks. So it's often the case that when you bring in a new framework and you bring this in because you need just a bit more lift or a new technique has come in, you can run the danger of needing to change production and therefore making it a larger change. With this technique that we're showing you, we'll show you that seamless switch from one framework to another, provided you follow the MLflow model practices we're showing here. So why is image processing difficult, we might ask? So just a few challenges here that I've seen. So with limited on-prem GPU available, sometimes it's super expensive to pull it in. It's a commitment. Once you develop a solution, all of a sudden to scale out, you need to buy even more GPUs. And then GPUs get updated, and then you're kind of stuck with that same hardware. GPUs are sometimes hard to architect and manage securely. So in your deployment processes, oftentimes you end up with large image repositories with just having a challenge of purely the number of image files. And so pulling those in through this technique with Delta Lake, we're going to show you how to kind of reduce that small file problem. And then it's hard to create structured table using unstructured image data alongside features. So oftentimes it gets overly complex to kind of build and run with images because you're having to assemble that from file. This technique, it'll all be a nice, tidy table, a lot less confusion and potential bugs, really, and then still be able to process and treat them as images when you need to. So using Delta Lake to store images, just a look at what we're going to do. So I'm going to start off kind of on the data engineering side and get these images ready for processing. And to do that, I've mentioned a few times that we'll be using Delta Lake. Delta Lake does a few things for us. So I mentioned the small files problem. If you're dealing with lots and lots of tiny files, your cloud sources and your distributed sources kind of get overwhelmed, or even directory listings won't work if you have too many kind of in the same folder. So being able to store files in the binaries for images in the Delta Lake is going to enable the fast inference queries. It'll keep down the files. It immediately gives you stream processing capability with virtually the same code as your batch. Gives you ACID transactions, so you can know that you have consistent data sets. And then you can even use configurable compression. So if you're dealing with images, as we will today, that are already compressed, there's no need to spend the extra time on read and write with taking care of that. So I'll show these off in the demo as well. And then kind of exploration versus storage. With Delta Lake, we support basically two kinds of formats. So there's a special, if you've read through the Spark docs, there's a special image format that is nice because, as you can see down here on the left, It shows the images, it generates thumbnails and processes. And that's really nice to look at a folder and full of images, or a folder with subfolders full of images, and really get a sense of what's going on. As it turns out, this image format is not necessarily the best in what we've found for processing images at scale. And so we like to use the binary format. It will use the image format for exploration, and then use the binary format to just keep it as a set of bytes. Keep the image as a set of bytes, and then alongside with some other features. And so that's what we'll go through today. The binary file will then we'll use it in various kind of Pandas functions directly, or in UDFs to work with the image. And then for further image processing, if you need to do stuff with the images and potentially with features and the images, we found that applying Pandas is a very convenient way to get this done. So you can have the luxury of integrating with your image processing libraries, Pillow or CV2 or something like that, while still being able to work at scale. Using this applying Pandas function, which we'll show you, avoids some of the technical syntax that itself can become a barrier to doing something beyond like a scalar UDF function. And then, like I said, it allows you to use the APIs that you're comfortable with. And so the basics of which you'll see during the demo shortly here are first, you just shape your schema to what you want it to be and use Spark for that. And then use your Pandas function. Applying Pandas operates using a group data set. So we'll group it by sets of images that you want to have at the same time, or maybe sets of rows that you're going to turn into an image that you're later going to turn into something else. Lots of different use cases there. But the short of it is, once you've defined your schema, and then you can call the apply in Pandas, you give it the return schema, and then you're able to join it efficiently. And doing kind of this process is how we've achieved some of the excellent speed up performance versus some on-prem and some other techniques that folks use. So with that, I'm going to jump into the demo and just show you what this looks like in Databricks. All right, so here is the Databricks workspace, and I've got our demo set up. I'm showing the workspace right now. I've got us in DAIS, and I've set up a few different notebooks here. I like to number them like this just to kind of keep them in order in my mind for whatever process I'm working on. But in this case, I pulled up the Explore notebook, and I've got that pipeline at the top. Nice thing about these notebooks, of course, is you can make them really rich, add in documentation and all that, while still being able to run them as production pipes directly from the notebooks. So some pretty cool functionality there. But without going into this is what we just covered on the slides. So let's jump into the data set a bit. So for this notebook, I'm just going to be showing you some of the features of the image file type. And you can see we're pulling in some PIL from image from PIL, as well as some of the Spark stuff. So for today's demo, we're going to use the flower data set. And what this data set is it's got photos of flowers, and they're in subfolders for the different types of flowers. So we have daisy, dandelion, roses, sunflowers, and tulips. And just to show off some of the functionality, if I use that image type that we saw on the slide and just point it at a directory that, in this case, I'm using Databricks, or I have a cluster running. So the cluster has access to that folder. then what it's going to show us is this nice visualization. It's going to generate the thumbnails for us and just kind of give us the ability to really scan through and see what's in there. You can always target that. So in this first one, we read in just a high level folder. The next level folder down is sunflowers, and so now it's only just going to pick up the sunflowers. And what you'll notice here is that when I read in a folder with subfolders, image is going to automatically assume those are a class, or those are a label, and it'll label them with the folder name. So then just kind of pushing through this, all right, there we go. We're going to push this over into Delta Lake. So as if I wanted to save that directly out so that other folks could do it, I could save that out as Delta. We're just going to push it into a data set, DAIS 2021 flowers train, and then make sure that other people can process on that. So in this case, I've taken that image file, that set of images directly from disk, and stored it out into a Delta table so that other folks can explore, and you can get these convenient thumbnails. If I look at that, we've got 3670 images in this one, so fairly small. You can kind of think about scrolling through and seeing the images, and it's fine. But when you get up to scale, you probably don't need all of that functionality. You'll probably be doing that only on the subset. But using the Delta functionality to optimize, you can see that we're going to take care of those files as they were loaded through the images method. Basically give you a chunk per image. And we've run optimize here to bring that down so that it comes into a more reasonable set of files for this much data, which is not a lot. So if as I'm going through this, I'm going to use that image format to explore things and kind of get a sense. But then when I'm actually building my pipeline, let's go through what that might look like. So if I switch over to Notebook 01 ingest, I've got ETL images into the Delta table. So in this case, I have the same set of functions. In my use case, I'm just going to use the image library, or the pill library to process images. We're going to now read the same directory, but this time we're going to read them in as binary files. And so in this case, we want to recurse, go down and look for JPEGs, which is what my images are in the source of. And then if I display that, you can see that we get a nice convenient data frame with the actual image file itself just loaded in as binary. And again, what that's going to do, as opposed to reading it in as a set of images, is it's going to give you, it's going to avoid doing all the processing that happens just so that we can display it nicely. So for large streaming use cases, this is probably what you're going to want to do after you have explored the data. So processing further, what we'll do here is we'll extract some features. So what I'd really like to do is give the class what kind of flower this is, look at the size, and maybe you'll want to do some other things. So in this case, we've just chosen a couple features to extract. We're going to use a simple UDF. So this is a scalar UDF to just pull out and give a string back or give an object back. With these two values. And so in this case, when I process, I do images, which is what we loaded in before, select. We're going to take in the path that was there. We're going to use those scalar UDFs, and then we're going to grab the content, which is the image. We do a step here. So in this case, we're doing this in the data engineering side. So we're going to change that label into an index. So you could do so that we can work with the numbers for the classes. And then at the end of this process, we're going to still end up with that same number of images, but now with a data frame that we can use efficiently using that binary object type. Let's pretend in this case that I have other image processing that I want to do. So in this case, I'm going to do a simple convert to grayscale. You wouldn't necessarily need to do that, but let's say you wanted to pull out the red filter and do something, do edge analysis on the different color bands, or whatever you need to do here. I'm just going to simply use the grayscale to demonstrate the apply in Pandas function. So if grayscale was what I chose to do, then what I've done here is I've defined two functions: get image bytes, which just takes an image and gets the bytes back so that I can save them in a column, and then a simple add grayscale image, which takes in a Pandas data frame and then adds a couple columns. So we're going to add grayscale image and grayscale format. Format is just going to be PNG, but we'll apply a function to this to take the original image and turn it into a grayscale. So if you look at this, all we're doing is doing plain old Python and then using the Pandas API, and then using my image library and IO bytes IO to convert between the binary string and something that's readable in a file looking thing for image processing. So once I have those defined, then I need to prepare my data set to actually call it and augment my data frame. And so to do that, we're going to set up a return schema. This return schema is not actually going to do anything. So there's no action statement in here. All I'm doing is using the select syntax and the with column to define the schema itself so that I don't have to manually type it out, and it can be more dynamic with my processing. So this return schema needs to match what the input or what the return value, this might say output data frame, but I was doing a one-to-one mapping, so I just returned it as input data frame. But whatever this function returns needs to match this return schema, and then the Apache Arrow integration with the apply in Pandas is going to make that all line up for you. So then I want to reduce my data frame. So if I have a data frame that might have lots and lots of columns in it, but I don't need all those columns for my function, the most efficient way to process that is going to be to limit your data frame just down to those elements that you need. So in this case, I'm doing grayscale, so I really only need content. But I'm going to group by label to send it across. So I'm going to do all daisies together and all roses together. That's just a choice, but you should have whatever you're going to group by in there. And then you'll need in this case, the path. You need to rejoin that data set back together because presumably you want to pull this in. Now, the reason I just don't cheat and send the entire data frame over is if there are a lot of columns, a lot of data, maybe other images in that row, depending on your application, that's just going to generate a lot of data serialization that you don't need. So doing this will keep it trimmed down and make the function super fast. And then using the power of Spark, both for the definition of the schema and the rejoin, this all happens really quick. Okay, so I've got my function, I've got my return schema, and I've got my cut down data frame. So now we just call it. So this is just going to be take that cut down data frame, group it by the label, and apply my function. And then you'll notice that the two things that I provide are the function and then the schema. And so what that's going to do is that's going to take that group at a time. It'll send out a group per task, and that will show up as a Pandas data frame here without you really knowing it or having to annotate it or anything. So it's pretty convenient. And you can see here that I've got my schemas called out, and ultimately I'm generating this as a data frame. So then just to finish that up a bit, oftentimes it's when you're dealing with your full data set, you sometimes need to debug this function without waiting all the time and then figuring out how to extract it. So I will often have potentially a commented out a testing section. So that's what I'm doing here. I've just dropped down to 10 rows and brought it in as a Pandas data frame. And you can see my chopped down schema here. And then in this case, I'm going to test the function directly. So I got my data frame. I'm going to call it directly. It's just Pandas, so there's no Spark involved. I'm doing all this on the driver just to sanity check my my function. And then at the end of the day, I iterate and do a couple subplots to compare the images. So for me as a developer now, I can see that my grayscale is coming across all right. I feel good with that mapping on the 10 images I looked at. So now I'm ready to loose the hounds and apply it across my whole data set. So I copy that or comment that out. But then now we can go and say, hey, let's run this thing. Let's take an action. Let's display the output DF. So when I do that here, I get my grayscale image created and my grayscale format. Because I've tested it, I'm confident that that's what I need for later on in the pipeline. And now I can go ahead and commit this to disk. I'm showing all this in a batch example, but all of this could be streamed. Simply with a change to write stream and change to read stream. So that's all possible, and the rest of the code stays the same. One thing to call out here is that if you're using compressed images already, so JPEG, PNG, others, you will probably want to save as uncompressed because that compression is already in your binary object. So if you have most of the features, if most of the data that you'll be storing is the images, then they're already in a compressed format, then it's a good idea to save off your current compression and set it to uncompressed, and then output write out to Delta Lake just like we saw before, and then restore your compression in case there's other things in your job. And then just like we did on the original flowers, we can optimize our write here. Given that we had pulled it in and processed it and it was tasked up nice, the optimize in this case didn't do as much because it's already being written to an optimal format. So hopefully that will help you with some functions and features that you'll be needing to do with imaging. It's really freeing to be able to treat images as kind of first-class citizens and also use your familiar APIs. So with that, I'm going to turn it over to my data scientist, Rohit, to take you through what somebody might do with this.
All right, thanks a lot, Jason. So now we've seen how we can ETL and ingest image data into Delta Lake. We've seen how you can, use the binary file format and optimize and avoid the small file problem. Now that you have a Delta Lake with images, the next question is, how do you build models? So let's say you build a deep learning model in one of the more popular, TensorFlow or PyTorch libraries. We will take a look at that and see how we do that, not just in a single computer, not just in a single machine, but in a distributed manner. With Databricks, one thing you can do is actually spin up clusters with multiple nodes, basically multiple computers all tied together, and each of it with multiple GPUs underneath it. So what this really allows is you can do distributed training of deep learning models. So you're not really waiting for one machine for a day to complete its training. Rather, you can do that in parallel at the same cost, much faster. This allows also for you to convert your single node deep learning model into a distributed training framework. So, you can take most of what you have, put it into a framework that I'm going to show you, and you'll be able to have that training run in parallel. And Databricks clusters auto scale, so you really only pay for what you're using. Now that you can see how Databricks allows you to create clusters that support distributed training of deep learning models, the next thing is how do you do it? So we do have frameworks that support distributed training. So a couple of the open source ones that are supported here are Horoward Runner, where you can do distributed training of TensorFlow, Keras, and PyTorch models. We also support Spark TensorFlow distributor in case your focus is really just on the TensorFlow side of things. And the last piece here is the fact that you can load your data using Petastorm. So let's say you have your data set as Jason showed you in let's say, a Delta table. You can use that Spark data frame and then load it into either a TensorFlow dataset or a PyTorch data loader format. So then you can feed that data into your deep learning framework without having to worry about that conversion from Spark or Parquet into your TensorFlow or PyTorch style dataset. Petastorm also caches the dataset in Apache Parquet format, and then it loads it either into the TensorFlow dataset or into the Torch data loader format. So again, really supporting the fact that you can feed your Delta table into these distributed training frameworks. One practical tip, and I'll cover this in the demo shortly, but we've seen that while loading the data using Petastorm, specifically the function called make Spark converter, where you feed in a particular Spark data frame and you create a Petastorm object that you'll then consume. In that process, you want to set a low value for this particular parameter Parquet row group size bytes. In our project, we realized that the default of 32 megabytes can be too high. Using 1 megabyte, as we see in the example below, is definitely a better option so that your cluster does not run out of memory. So that's a nice tip we learned. And here you see in the screenshot below how we use Horoward Runner that I covered in the previous slide to do distributed training over 2 worker nodes. Once we do distributed training and you have a distributed, you have a deep learning model that is ready to be used, the next question is how do you actually use it in an inference pipeline? As Jason alluded to earlier, we'll see how MLflow actually supports that and supports that in a way that, if you, as a data scientist, you build your models using whichever framework you like, whichever underlying, parameters, frameworks, whatever that is, MLflow will allow that particular model to be used in a generic format so that the inference pipeline is actually not going to be affected if the underlying model type changes as a data scientist trains and tries out different models. So MLflow's model registry, and specifically when we track a particular model, be TensorFlow, PyTorch, or many of the other ones, open source ones that are out there, apart from registering them in the original format and flavor, we also support what is called a PyFunc model flavor. It's a generic Python function-based flavor, which then allows the inference pipeline to be completely isolated from the training pipeline and whatever model is used. So as a data scientist, I could switch from TensorFlow to PyTorch and nothing would change in the inference pipeline. And I'll show you that in just a second. The other thing to understand here is when we run inference using MLflow and Databricks and Delta, you can do distributed inference so that multiple nodes of your cluster is running the inference. It's applying the model in parallel, and you can do that either in the batch mode or in a real-time streaming mode. And we'll actually show both of those in a second. And as Jason mentioned, you could also deploy these models to an edge device. So let's say you just want to train it using a set of GPUs within Databricks, but your end use case is elsewhere. You can use MLflow to even do that sort of a deployment of the model to edge devices. With that, I'm going to switch over to the demo where I'll walk you through both the training pipeline as well as the inference pipeline. So here we are now looking at the Databricks UI. And before jumping into the training and the inference pipelines, I just wanted to quickly show you what a cluster that we're using would look like. So as you can see here, I'm just going to walk you through the key pieces that matters. I've selected the 8.2 ML. So that's basically an optimized runtime that Databricks provides. It has a lot of the machine learning packages pre-installed. And you can see here, it has GPU support. So that then allows you to pick GPU instances. As you see here in the driver and the workers, I have, in this example, the standard NC24, which has 4 GPUs and whatever the memory is. And we've set the auto scaling and auto termination enabled. So it can, as it senses workload, it can increase the number of workers from 2 to maximum of 8 as required. So the key idea here being, this is available on multiple clouds. So depending on the cloud that you're in, you can spin up secure clusters with GPU very easily using just a couple of clicks within Databricks. And now that we have this cluster ready and running, I'm going to switch over to the very first pipeline, which is the TensorFlow training that I wanted to walk you all through. So as you can see here, we'll take a look at some of the steps. The very first is how do you load that data into Spark? And then once you have a Spark data frame, you want to convert that either to a TensorFlow data set or some other format. And for that, we'll use Petastorm. We'll use make Spark converter. Once we do that, we'll then take a look at the example where we train a single node TensorFlow model. So that's something you may be already familiar with, the kind of stuff you might be doing on a single virtual machine. Once we do that, we'll then use that to then train that TensorFlow model in a distributed manner across this cluster we just showed you across the multiple GPUs in this cluster. So kind of scrolling down here, we'll start off by setting where we want to track MLflow experiments. So as you build and iterate on different types of models and parameters and so on, you can track all of them automatically. You can see here, I've also set a couple of other parameters for MLflow. One is TensorFlow Autolog and Spark Autolog. So what these will do is, as you train experiments, it's automatically going to track what is it that you're running, what are the parameters, and what are the metrics, validation metrics, and so on. So it makes it really easy for you as a data scientist to then go back and see, okay, this is what I ran a couple of days ago. These are the parameters. It'll also give you the version of the notebook. So it makes it very easy to kind of go back and reproduce experiments. So it gives you a good way to automatically track your experiments. We've set a few parameters here, including image shape, batch size, and number of epochs. So these are your standard TensorFlow parameters. We'll see how that's used. So going to the first step, we are going to be looking at how we ingest the data that Jason has created and curated for us. As you see here, I'm just reading it in Delta format, the flower strain binary data set. So since we are actually in the production pipeline here, we want to use the binary format of the image data set. And I'm picking some columns that I want, and we are actually repartitioning it. We want to make sure that there are at least as many partitions as there are workers, if not more. Once we do that, once we've ingested the data set that Jason created for us, the next step is then to make a Spark converter Petastorm object. So what this really does is, for each of your train and validation set that we created, you can see here, we use this particular function, make Spark converter. We feed in the Spark data frame and the particular parameter Parquet row group size bytes that I was referring to earlier. You want to reduce that down to about 1 megabyte. And once you do that, you can then use this object within your framework to get a TensorFlow data set and build your model. So that's how you use Petastorm to convert a Spark data frame into something either TensorFlow or PyTorch can understand. What Petastorm also does is it creates a cache. As you can see here, we've listed the cache on DBFS, and you just specify the particular folder, and it'll save that particular, whatever is being ingested in a Parquet format, so then it can easily reaccess it pretty quick. Once we do that, the next step then is just to check how many records we have. This is just a sample. So I have 71 training records and 29 validation images. Again, one idea we wanted to also help users understand is, for deep learning models, you don't necessarily need to have terabytes. If you have, that's great. You can probably get great value out of it. But even if you have small data sets, you can use pre-trained models, as you can see here. So it's basically transfer learning. In TensorFlow, we have this MobileNet V2 model with weights that it learned from ImageNet. We'll just pull that model, we'll take out its last layer, and we'll retrain it on the specific example that we have. So what that helps us do is it avoids the problem of having to gather terabytes worth of data in case you don't have that. And you can just use one of these models that have been trained on publicly available data sets, and it's been tried and tested. So that's what we're going to do here. We'll ingest, we'll pull in the MobileNet V2 model from TensorFlow. We'll provide the parameters of the input data set, which is 224 pixels by 224 by 3 color channels. And once we do that, you can see the summary of the pre-trained model that we get from TensorFlow. Once we have that model ready, the next step we're going to do here is then add that last layer. So we are adding one dense layer at the end, and we'll make sure to train that with the specific classes and the specific data that we have. So it's more applicable to what we're trying to do here. Once you build the model, the next thing is obviously to compile it. So depending on the parameters you set, in this case, we are doing stochastic gradient descent, providing momentum, as well as what metrics we wanted to optimize on. And we are obviously using categorical cross entropy, as is quite common. Once we do that, you can then again take a look at the summary here. It clearly shows that it's a mobile net v2 followed by a pooling layer followed by a dense layer, and the number of parameters corresponding to it. Once we have that ready, the next step is then to pre-process the images. So we have a lot of images, that are stored either in a binary format or in some cases just the path to the image. But in this case, starting with the binary format that Jason provided us, the first step we want to do is we want to do a transformation so that it conforms to what ImageNet expects. So we'll do that here. As you can see, we are first of all using bytes.io object to decode the binary data, and then we open it using Python's image pill, Python imaging library, pill library. And once we open it, we'll then resize it and use Keras pre-processing to then convert it to an array. And once we have that, we will then feed that into the next layer. So as you can see here, in the next function, we're transforming each row. We're using a map. This is, again, all of this is just regular Python code. We are using a map and applying the function that we just defined up here to each row. That will then do the transformation on the content column, which is where the binary data was stored. Now, once we have that, as you can see that we've listed here, our recommendation is actually not to do this directly on a Spark data frame because it can generate substantially large intermediate files. What would definitely be recommended is to then create a transform specification that Petastorm can then use. So as it loads the data from the Spark data frame, it'll do these transformations and then feed it into the TensorFlow or PyTorch framework. So it makes it pretty easy to do that transformation as it's loading in the data. So that's what we're doing here. We'll just provide this particular function. We'll provide the fields that we've changed, as well as the final set of fields, which is features and label index in this case. Once we do that, the next step here is to then create a custom wrapper. So this is the piece where MLflow will allow you to isolate your inference pipeline from the training pipeline. So even though I'm developing a TensorFlow model, what I ideally want to see is, it's a model that's wrapped in a generic Python function flavor, so that the inference pipeline does not need to know what is going on underneath. Is it a TensorFlow? What are the parameters and so on? So what we're going to do is we'll create this custom class, this wrapper class, that will extend the MLflow Python model flavor. And we need to do one thing here, which is to define a predict function, a predict method rather, that will then do the transformation. So what we'll assume is when we use this particular trained model in the inference pipeline, we'll just provided the data in the raw format. And when we say the raw format, it could either be the binary or the path to the file. You'll see in our inference pipeline, just to kind of mix it up, we show you an example how you can use the path to a file and feed that into a predict function. And then within the predict function defined below, it will take into account all the transformations that we need for the specific framework. So right now we're using TensorFlow. So we want to make sure that for the TensorFlow model that we've created, it is able to use that as a tensor. So we make sure to do some of the pre-processing, mapping, for example, mapping the class definitions from the text name to the numeric index, making sure that the path to the file has the correct DBFS. It's what we call as a fuse mount, using the fuse mounts here, and then creating the structure of what I want to return here through my function, through my predict method. And once I have that, then I'm going to iterate through my input that is being passed in this case, the set of paths. I'm going to go through each path, each file. I'm going to open that, do the transformations that is required, use TensorFlow's reshape function to reshape it, and then feed that tensor into the model so my TensorFlow model can do the prediction. So that's what it's doing here. What all of this really is trying to do is basically make sure that, we make sure the data scientist is doing the transformations that TensorFlow expects. So rather than having the inference pipeline do that for us. As you can see here, I'm returning two things. One is the prediction, as well as the probabilities corresponding to each class that we expect to predict on. Once I've defined this wrapper, I'm then going to use it in the training pipeline down here, where I'll wrap the model that I've trained with and then log that into MLflow. So let's take a look at that. So this particular function is going to be running the training, but on a single node. We'll start with that. That's an easy way to then step up your development, then to into a distributed framework. So always try starting with a single node framework. So we'll do that. We'll first of all consume the converter train and converter validation objects that Petastorm provided, and we'll make a TensorFlow dataset out of those that will provide it with a specific batch size, and it applies the transformations that we just saw earlier. Once we have those two pieces ready, the rest of it is really the regular TensorFlow code here. We're mapping from the input to the features and label index, making sure that we have the correct batch size, and which really drives the steps per epoch, as well as the number of validation steps. And once we have that, then as you would have already seen earlier, you can do the TensorFlow.fit and provide the train data set as well as the validation data set and these other parameters. Once we do that, it'll train the model. And now that we have a trained model, the next step, what we want to do is to then log it within MLflow. As you can see here, I'm pulling in the run ID and experiment ID from MLflow. And I'm also making sure that I wrap this particular model that I just created using the custom wrapper class above. So you can see here, I'm using the run ID and experiment ID, and I'm pointing to the model. And once I have this wrap model, I'm then logging that as a generic Python function. And you can see here, I'm calling the Python model equal to wrapped model. Once I do that, I now have something that's stored in a way that any inference pipeline that supports MLflow can easily use without knowing what's going on under the hood. So now that we've run this, as you can see here, we trigger the run with MLflow.startRun and call this function. So it runs through that. Again, this is a single node process, and it's just a simple example. It's not something that's the most accurate of trying to find the best architecture. That really depends on what you're trying to do and what your use case is. But now that we've trained this on a single node, what we can see is I come here onto the experiments, and it tracks all the different experiments I've been running, and it'll tell me which one corresponds to what. I know this is the one that I used from this particular TensorFlow example, so I'm going to open that up, and it'll give me everything corresponding to this particular model run. So let's take a look at that. You can see here within MLflow tracking, it tells me which is the source notebook. It actually has the version of the notebook that was used. So if you want to reproduce your run, you can easily do that. It tells me all the parameters that we use. So when we call mlflow.tensorflow.autolog, it captures all these parameters, including the default ones. It has the metrics as well from the training that we called. And it has tags, some of which are pretty useful. So you can actually go back and use a version of that delta table, like using time travel, and go back to an earlier version. So in this case, it is version 5. So even if somebody, ETL pipeline is running and that particular table is changing, you can say, hey, give me the version 5, and you can recreate your experiment. So that's pretty powerful in that, you can, you have the code, you have the parameters, and you have the data source that you can use to recreate it. Coming down here on the artifacts that are stored, we can take a look at some of these things. So it stores the model summary, as you can see, the mobile net and the dense layer that we added. It stores the original TensorFlow model that we created. So this is the one without any wrapper around it. As you can see here, by default, we save 2 flavors of it. One is Keras, and the other one is a generic Python function. But much more interestingly, for us to be able to use this in an inference pipeline, I close this one and I use and we can take a look at the version where we actually wrapped it with that custom class with the predict method. So you can see here, it's just the generic Python function flavor. So you can see that we've saved everything that corresponds to our particular training run in TensorFlow, and switching back here. Coming down here, before we move over, I just want to quickly walk you through the example where we actually train the same model, but over a distributed cluster like what we have here, and doing it over all the worker nodes and the GPUs within it. So for that, we use this particular framework called Forward Runner. And with Forward Runner, what it'll do is it'll actually make sure to distribute the entire computation. And to do so, you need to make sure that you set up these callbacks that Forward Runner supports. And once you enable the callbacks, you can see the rest of the functions are practically the same thing as we had earlier. And I'm really using most of my functions from earlier. So you can see I'm not having to redefine my model or my framework. I'm just making sure that I do the retraining, but this time in a distributed manner. So when I do the fit method onto the model, apart from the training data set, validation data set, I also make sure to provide the callbacks. Once you do that, as we saw previously, you just do a .start run and call Forward Runner, and you provide this parameter np2. So in this case, it assumes a cluster of 2 worker nodes, each having its own GPUs. And once you do that, you just do a hr.run and call this particular function that we just defined up here. Once you do that, you can see that it does the distributed training of the particular model we saw. Now, all of this was an example where we have the raw data in binary format. But let's say you actually have very large data sets, each of which with very large images, and you'd rather not store it in a binary format. What you can then do is actually create a Delta table that contains the path to those files rather than storing the binary data itself, and just linked a couple of blog and notebook that you can access later to see how that works with these frameworks. Now that we've seen this, let's kind of switch over to the particular model. What I've done here is I've already registered it into the MLflow model registry. So in the MLflow model registry, we are able to track what are the different versions of our model. So in this case, you'll create one logical model for our project. So I've called it Data and AI Summit, Image Classification. And I have this version 1, which is the TensorFlow version that is currently in production. So, you can apply governance. So only an admin can actually move it into production and staging. But as a data scientist, I could make a request to either move it into prod or staging and so on. All of this matters because you can then apply that governance. So, your data scientist not doing a science experiment and then deploying it into production and breaking things. We'll see in just a second how this matters for the inference pipeline. So let me switch over to the inference pipeline here and show you what this looks like. So on the inference side, I'm going to read a particular table. In this case, I'm reading something that is stored in the image format, but in reality, that doesn't matter, because if you unclick this image preview, you will see that it's really storing an origin object, which has the path to the file. And that's what we're really feeding into the predict method. So, at the end of the day, if you have the location to the files, you can easily call this particular TensorFlow model without having to worry about, which format and, decoding the data and so on. In this example, because it's a dummy example, I just have the training data set that I'm reusing, which is why you see the label, but obviously in a real pipeline, you wouldn't see that. So we'll ignore this label, but we'll still use the path to the file and score the images. So this is the inference pipeline where, I want to use the model that I've saved in the MLflow model registry. The way you use a particular model is just call models, / and the model name. So that's the one that we just saw here, Data and AI Summit, image classification, that's what I call it. And you just say, hey, just give me the production version, right? I don't care if it's version 1, version 10, it doesn't matter how many iterations, just give me the latest production version. Right now, you can see here, I have this one as the production variant. Once I do that, I then load that as a Spark UDF. So you can see here the way you call it is using mlflow.python function, the generic Python function, and load it as a Spark UDF that I can then use in a Spark data frame. You just give the file path as well. Once you do that, the last piece here is just calling your, using your test data set and calling this particular Spark UDF down here. And what I save that in a my predictions column. To visualize that, you can then just do a display on it. And you see here, I now have the predictions from my TensorFlow model that are saved here. And it gives me the two values that I need, the prediction as well as the array that contains the probabilities for each of the classes. Now that we've seen an example of how you create a model using TensorFlow, train it in a distributed manner, and run it through the inference pipeline, let's take a quick look at a PyTorch example. It really covers most of what we did in the TensorFlow as well. So you load the data, use Petastorm to create a PyTorch data loader, train it in a single node example, and then use that to then do a distributed training. So in the interest of time, we're going to quickly go through this and not go into the details here, but we'll do the same steps, load the data, feed it into Petastorm. We will use the MobileNet V2 example, add a last layer to it. We'll define the train and evaluation functions. And after that, we'll then do pre-processing of the images, like was in the example earlier. Again, feed that into a transform spec for Petastorm. And once you do that, then you can see we've also defined a custom PyFunc MLflow class, a wrapper class that you can make sure it'll do all the transformations that are PyTorch specific without having to worry of what these transformations are in the inference pipeline. So again, this is super critical. So make sure that your inference pipeline is isolated from the training framework. Once you have that, you then just start off with the single node training. Most of this is your PyTorch code, so I'm not going to go through it. It really depends on what framework you use. But the key pieces are you can then wrap that trained model and log it into MLflow. You can see here I'm also transitioning that into staging. Once we do that, you'll also see there's an example below of using Horoward Runner, so the same framework to do a distributed training of PyTorch over the GPUs on the worker nodes of this particular cluster. Now that we have the second PyTorch example, let's take a quick look at what that means for us in the model registry. So this was transition. So I manually clicked and transitioned this into production. So now that I've switched over from TensorFlow, which was the V1 that was in production earlier, I've switched over to V2, which is the PyTorch, into production. And once I do that and go back to my inference pipeline, the inferring logic doesn't change at all. So it's just going to pick up the latest version from production and it'll apply the model to the test data set. So it's pretty nice to see that that transition from TensorFlow to PyTorch does not impact your inference pipeline at all. You'll also see there's a streaming example, which really looks very much the same as the other example with just a read stream and write stream. With that, I'll pass it back to Jason for wrapping our talk up.
All right, thanks, Rohit. And I'll just take us home here, just going over a couple limitations. So we've seen today using Delta Lake directly for the image binaries or pulling up through file system. For the binary version, if you have very large images, then you're going to blow past the Delta Lake default block limits, which are up to about 2 gigs. So we recommend using this technique if your images are 512 meg or less. That's a pretty big image. So if you have something bigger than that, maybe it makes sense to chunk it up and be able to use the binary formats, or just switch to the file format as you saw in the model example. So in summary, you can use Delta Lake. It's a very good thing to use for storing images. Helps on the small files problem, as well as gives you faster inference queries, particularly for images 512 meg or less. MLflow allows us to separate, along with the custom MLflow class, to separate the inference pipeline so that you can bring in, as a data scientist, whatever model framework works best. And then if you're running this on Databricks, we can really efficiently support distributed training and inference over hardware that matches whatever cloud that you need, giving you a consistent pipeline and a consistent run wherever your data is. So I hope you have enjoyed the presentation. It will be helpful for you. And we look forward to your feedback on this session.